So this is about the monopole thermal Hall effects in pyrochlore U1 spin liquids. So the storyline is here. So the pyrochlore U1 spin liquid is described by emergent and compact U1 electrodynamics or compact U1 electric schedule theory in 3+1 dimension. So the observation is that with the Zeeman coupling, magnetic field, the Zeeman coupling, the external magnetic field will polarize the spin a little bit and effectively generate the internal electric field distribution. So this internal emergent electric field distribution, if you do electromagnetic duality, so this functions as emergent dual U1 gauge flux for the magnetic monopoles, and as a result, the magnetic monopole will acquire non-trivial barrier curvature, and this is reflected as the thermal Hall effect. Essentially, so this is the topological thermal Hall effect of the magnetic monopole, which is the topological excitation of U1 pyrochlore spin liquid. So the topological excitation in exotic phases. So this work is in collaboration with my postdoc Xiaotian Zhang and my former grad student Yonghua Gao and Chenxiao Liu. So we are writing a review paper on thermal Hall effects, and it will be come out I believe quite soon. The content of this talk is mostly in this paper, this PR research paper in 2020. So let me first give some few backgrounds about pyrochlore U1 spin liquids. So we know, as we all know, this is spin-ice spin configurations, and it describes the Ising spin configurations with 2 in 2 out on this tetrahedrals on the pyrochlore lattice. So this is a highly degenerate classical spin liquid, classical spin configurations. And thermal, if you turn on temperature, they can thermal fluctuation among all these highly degenerate manifolds. So, but we're not interested in this classical limit. We're interested in quantum mechanics. So pretty much if you add on some transverse field, transverse exchange, so or any other kind of quantum perturbations or general quantum fluctuations among these degenerate spin-ice configurations, as long as these perturbations are not significant enough to induce magnetic order, one can obtain a U1 pyrochlore spin liquid. And this is this energy scale distribution of these emergent quasi-particles in the pyrochlore U1 spin liquids. So we have 3 different quasi-particles. At highest energy scale, we have these gapped spin-ons. At the lower energy scale, actually much lower energy scales, we have magnetic monopoles and emergent gapped gauge photons. And these 2 are of similar energy scales. So this is a sketch of this spin-on deconfinement in the pyrochlore spin liquids. So these spin-ons are so-called topological defects of this spin-ice configurations that violates spin-ice rules. So essentially, if you can break these spin-ons apart and separate them to be arbitrary distances, they only cost the finite energy. And spin-on are deconfined. And spin-on are, it has a classical analog, which is connected to this Mersner's original idea of classical monopoles in classical spin-ice. But the magnetic monopole I'm talking about today is a pure quantum mechanical object. It has no classical analog. It's a topological defect of the vector gauge potential. So we'll see that more clearly in later slides. So on the experimental side, there has been actually a lot of experiment on this pyrochlore material, pyrochlore rare earth manganese, pyrochlore U1 spin liquid mechanical materials, but not much on the thermal Hall effect. A thermal Hall effect has been widely discussed in the cadaver materials, as we have seen in yesterday's talk. But not much on these pyrochlore spin liquids. I think one of these very early experiment, it was performed by Max from On's group, and he talked about ytterbium yesterday was ordered. He did not talk about this terbium today, which is dissolved all the way down to lowest temperature. And it was proposed as a pyrochlore quantum spin-ice this material by Ginger. And this is the thermal Hall measurement, and it shows a non-monotonic dependence in temperature. So these levels at temperature and also on magnetic fields. So nanomolecular on temperature and magnetic fields. And the thermal Hall conductance persists to very high temperature, and paramagnetic regime without any quasi-particle-like transport, and also breaking down of the effective pseudo-spin 1/2 description. So even above the temperature where the pseudo-spin 1/2 description breaks down. So this is some little facts about terbium titanate. The most important one is so the effective spin 1/2 for the low temperature, for the very low temperature magnetic property is described by a so-called non-quantum doublet. Yeah. So this is another measurement by Eugene Batuta in 2018. This is not a thermal Hall measurement. This is thermal measurement, thermal conductance measurement, carbon X in praseodymium zincnate. It's also a non-quantum doublet. So he found a correspondence between the thermal conductance and the energy scale distribution of these quasi-particles here. So at high temperature, believed to be a spinon-like excitations. At low temperature, there is hump, and this hump is attributed to this monopole and gauge photon contribution to the thermal conductance. So this looks very promising. So now I want to switch gear to say a few words to make some higher level general remark on thermal Hall effects, quantized and unquantized in exotic quantum spin liquids. I listed several different cases for thermal Hall effects in quantum spin liquids. First is which is well known in chiral spin liquid. We have chiral programming edge says we have we are sure you have quantized thermal Hall effect. The second one is this gapless D2 spin liquid. The spin-on sector is gapless, the matter sector is gapless. So if we apply magnetic field, presumably magnetic field could change the spin-on band structure topology. For example, create a chiral edge mode for the spin-ons. And this happens for Kilab spin liquid. This Kilab spin liquid is such a case where magnetic field drive a topological transition, topological band structure transition of the spin-ons and create a half quantized thermal Hall effect, right? So the third case is gapped Z2. So magnetic field will simply rigidly modify the spin-on bands. It may obtain quantized or most generically is the unquantized thermal Hall effect. The more interesting case, or I believe, is probably more interesting case is this U1 spin liquids. So where the gauge sector is continuous rather than discrete Z2. So external magnetic field, in the most interesting case, comes in and modify the internal continuous U1 gauge part of the action, and thereby modify indirectly twist the motion of the matter fields like spin-on or monopole and generate thermal Hall effects. So this includes the spin chirality mechanism, for example, from DME during schematic interaction and or the charge fluctuation in a weak model regime. So that was quoted by Max yesterday. And this thermal Hall effect in the fourth case is generically unquantized. It's not going to be quantized at all, but still very interesting. Now let me switch back to U1 spin liquids from particles. So in this particle, the representative model is this XXC model, and you can add some other for the neighbor for the perturbation. It doesn't really make much difference. So if you do perturbation theory, you get a ring exchange, and turns out that these Z component of the spin is identified as the emergent electric field that connect to the center of these neighboring tetrahedrons. And this transverse component is identified as weak gauge potential. So the intermediate or to low energy physics is captured by a low lattice gauge theory with magnetic field like term and electric field like term. So this is like electrodynamics, E field term, B squared term, right? So this is lattice gauge theory, and this describes lattice gauge theory on the diamond lattice formed by the center of the tetrahedrons. The center of the tetrahedron of the particle lattice is a diamond lattice, right? So what's the insight? So we want to understand. We want to generate thermal Hall effects. How do we how does thermal Hall effect comes? What's the law of the external magnetic field? As we remarked earlier, so magnetic field need to come and modify the internal gauge field, right? So how do we see that? So we need to see that we need to we need to do some kind of transformation. This is called the electromagnetic duality. We know Maxwell equation is self-dual in the absence of electromagnetic, in the absence of current and source charge, right? So here we have make use of this electromagnetic duality. So to do this duality, you can make this magnetic monopole, which is the topological defect of the vector gauge potential. You can make this monopole explicit, and turns out that these dual magnetic monopole are living on the dual diamond lattice. So the dual lattice of diamond lattice is also a diamond lattice. So the magnetic monopole lives on the dual diamond lattice and minimally coupled to the dual U1 gauge field. Magnetic monopoles see the electric field as a flux, just like the electron see the magnetic field as flux, right? Electrons see the magnetic field as flux, and the magnetic monopole see the electric field as flux, right? So as we said, SZ, the Z component of spin is electric field. So when one applies magnetic field, it will polarize the Z component of the spin, right? So it will generate a non-zero, create a different electric field distribution. So we'll modify the background electric field, right? As a result, so this monopole that hops on the dual diamond lattice will see a different electric field. As a result, a different dual U1 gauge flux, right? So the weak magnetic field polarize the spin slightly and modify the background electric field distribution. So this further modulates the monopole band structure and creates a generically Hofstadter-like monopole bands. And this may be declared by neutron scattering, but it doesn't really matter, right, for our purpose. So this making use of this electromagnetic duality, one can see the external magnetic field induce the internal E field. So induce the internal E field, internal electric field. And this internal electric field twists the motion of the magnetic monopole and generate a responsible to the thermal Hall effects, right? So this is another way of seeing it. So originally we have this minimally, so this monopole hopping on the dual lattice minimally coupled to the dynamic U1 gauge field, but with Zeeman coupling, so the magnetic flux, the dual U1 gauge flux is no longer, in this case, pi flux with time Wilson invariant, but with magnetic field, so it's no longer pi flux. Will generate a monopole band curvature. So the E field is no longer the original one. There is an offset due to the external magnetic field. So the monopole band structure, monopole hopping Hamiltonian will be modified. So the monopole see the electric field as a dual U1 gauge flux. So dual U1 gauge flux generate the monopole band curvature, and monopole band curvature is reflected in the thermal Hall transport. And this is the calculated result of temperature dependence of the thermal Hall effect, thermal Hall conductance. So the induced U1 gauge flux is generically incommensurate, right? Is incommensurate, but it really doesn't matter. It creates some difficulty in the calculation, but one can choose some commensurate one to do some calculations. So the field dependence is also non-monotonic because large field destroy the state and enter a fully gapped regime. So what's the application? So this theory, this monopole thermal Hall effect, directly applied to the pyrochlore U1 spin liquids with non-chromous doublet. For example, terbium tenonate, personium zirconate, personium hafnium. It also applies to pyrochlore U1 spin liquids with chroma doublet. So one may worry about the spin-ons, right? So if you ask, I will give you more comment on this. So for chromous ions, so the magnetic field will couple to both the Ising Z component of the spin and also the transverse component of spin. So that created some difference, right? So for new doublet called the octuple double doublet is a recent fashion. So in dipole U1 spin liquids, this theory was also applied, but for octuple ones, the theory is different. Yeah. So let me summarize. Yeah, I'm on time. So thermal Hall effect is a revelation of the intrinsic coupling between the various emergent degrees of freedom. Right. In this case, it's this monopole dual U1 gauge field coupling. When you apply field, you twist it, you generate intrinsic internal U1 dual U1 gauge flux, and twist the motion of the monopole and generate the monopole battery curvature and giving rise to the thermal Hall effect. So to tackle them, to understand them, we need to understand both the microscopics, what the behavior of the spin degrees of freedom, how do they couple to the external magnetic fields, and the emergent physics, the connection between the spin degrees of freedom, spin variable, and the emergent E variable, emergent B variable, emergent vector gauge potential, and establish the connection between them, right? So the physical, apparatus like a magnetic field, etc., is applied to physical degrees of freedom, but we want to see the effect on the internal degrees of freedom. So to understand that, we need to establish the connection between these, physical degrees of freedom and the emergent degrees of freedom, right? So monopole thermal Hall effect in pyrochlore U1 spin liquids is the illustrative example of such understanding, right? So for more, please refer to our forthcoming review work. Thanks very much.
Very much. I think we can stop here. Okay. Thank you, Gang, very much. Can you go to one of the first slides where you discuss the different types of spin liquids?
Oh yeah. Let me do this. Here we go. Here, right?
Yes. Yeah. I'm actually not so familiar with the key type system. So when we apply the in-plane field, it becomes gapped, right?
It becomes gapped. Yeah, it's a topological transition. Yeah.
So then we have a chiral spin liquid with a gap in the in-plane field. But you say the zero field state would be gapless and already have a thermal Hall effect?
No, the zero field is gapless. It's not really. No, so I'm saying, thermal Hall measurement is performed with magnetic field, right? So for gapless Z2 spin liquid, so the way to generate the thermal Hall effect, you apply magnetic field, right? For type case, you originally is a gapless Maillard fermion. You apply field, you modify the band structure topology of the Maillard fermion, and you gap out of them. You create a Majorana edge states, and that contributed to half quantize the thermal Hall effect, right?
And the U1 spin liquid is always gapless. Is that correct?
Yeah. So in the second case, I'm considering a gapless Z2 quantum spin liquid. So the rule, to obtain quantize the thermal Hall effects, the way to do it is the magnetic field comes and modify the spin on band structure topology, right? That will give rise to quantized thermal Hall effect. That's the mechanism. Yeah.
Thank you.
There's another question in the chat. I don't know if you can see it. I can read it if you want. So
how does the DM term or Kitabi term affect the dual gauge field monopole curvature? Well, this is not very particularly relevant, I think, but it doesn't matter. So the model here is not really involving DM interactions. But if you write down this microscopic Hamiltonian in the global coordinate basis, you can have these DM interactions. But the I don't think DM interaction matters here. I don't think it matters. Yeah.
Can I ask a question?
Yeah.
So, hi, this is Ipin. So, I'm curious about, like, in order to see this effect, does that mean like the temperature scale to see the non-trivial behavior should be comparable to the magnetic monopole temperature scale?
Yeah, that's a good point. Yeah, that's right. So in order to see that, you need to make sure, at least make sure these one can use monopole as a well-defined, more or less well-defined quality particle, more or less a good quality particle to capture the transport, right? So if you apply field, if your magnetic field is strong enough, if your temperature is large enough, the thermal fluctuation will kill the state, right? So then this quality particle gauge coupling picture is no longer a good description of the low energy physics. So you cannot use that to capture your transport, right? So this in this regime, this is called the transport of M particle. So we need to think about some other formalism to understand it, right? This is also precise the reason I believe spin-on thermal Hall effect in particle ice spin liquid is may not be applicable because in order to access the spin-on thermal Hall effect, you need to go to a very high temperature, and at this temperature, so the state is already be killed, right? So you cannot use a spin-on gauge coupling to capture the thermal Hall temperature, thermal Hall transport in this temperature regime, right?
Okay, thank you.
Is there another questions from anyone else?
The only difference between Chiral spin liquid and the Chiral Z2, a gapped Z2 spin liquid with a non-zero chirality? That's a very good question. There is a difference. So for chiral spin liquid is described by Chen-Simon, Chen-Simon field theory. The starting point of the gauge theory is a U1. So for chiral Z2 spin liquid, the gauge cycle is rigid. It's also rigid. Well, for the Chen-Simon field theory, it's also rigid, but it's U1. But for chiral Z2, the gauge cycle is a Z2. So there is a Wison excitations. And what happens is the chiral here is applied on the spin-ons rather than to the. Yeah, there is a difference, but it's not it's still quite different. So the chiral here is the spin-on band structure pick up this non-trivial topology, but it doesn't really generate this Chen-Simon term for the chiral Z2 spin liquid. And in addition, we have this gapped Wison excitations, which is absent in the chiral spin liquid. Yeah.
Sorry, Gama, one more question. My question is the actual proposed experimental geometry. This is a very naive question, I guess, but you're saying we should make a plate-shaped sample and then put some gate electrode on top and apply some DC electric field and measure the thermal transport perpendicular to the electric field, right? Is that correct?
Oh no, the field is magnetic field. It's a magnetic field. It's not an electric field. So the electric field is emergent electric field. So it's because this particle U1 spinning is described by emergent electrodynamics, right? So the B field, this external magnetic field B, which induce finite SZ, which finite SZ is finite E field distribution. So I mean, you are doing the same experiment as you always do for thermal Hall measurement, except the way your magnetic field, your applied magnetic field influence the internal emergent degree freedom is very different, right? So that's the key, right? So the role of the magnetic Zeeman coupling is quite different for different spin liquids, right? That's being emphasized, I think, in this general remark. Yeah. Yeah, for instance, in this spin chirality mechanism, because the spin chirality, this is scalar spin chirality, you want spin liquid is nothing but a gauge flux, a U1 gauge flux, right? So this U1 gauge flux can be due to strong charge fluctuation or due to combination of DM interaction and Zeeman coupling, right? So basically, you apply field, the field generated for the charge fluctuation can you generate uniform spin chirality or generate uniform U1 gauge flux. For the DM interaction case, it will generate non-uniform gauge flux because DM interaction depends on the bond geometry, depends on lattice, right? So, but always it will generate a U1 gauge flux distribution, right? So for this particle U1 spin liquid, the theory is the spin chirality is not so this flux is not a spin chirality, which is not a scalar spin chirality. It's this linear component of spin. It's the linear component of spin. So Zeeman coupling directly induce a internal dual U1 gauge flux. So that's the key, right?
We have one last very quick question.
Thanks for the nice talk. So in this calculation, I guess you assumed this assume that these monopoles move independently from each other. But are there any like attractive interaction between monopole and anti-monopole?
Yeah, no, that's a good question. So we're doing, yeah, we are, yeah. So in this calculation, in this particular calculation, we are assuming independent free non-interacting monopoles, monopole gas, essentially monopole gas, right? Right. So that works because it's gapped, and we are not trying to condense them, right? So there are interactions between them. There are, if model become dense, for instance, if you approximate to a confinement transition, when SZ is almost development magnetic order, then multiple number become dense. The distance between them becoming very short. So you need to worry about strong interactions. And that's actually quite important. The multiple interaction is responsible to the type of magnetic order that be induced.
Deconfined phase.
It's a confinement transition. Yeah.
How do you control that? How do you make sure that you are in the deconfined phase?
Oh, how make sure I am in deconfined phase? Because U1 spin liquid is a deconfined phase to start, right? So we are sitting in the phase. We are sitting in the phase and doing the calculation, right? We are not really going to all of the phase, but in all of the phase, we're doing something different. We're doing spin waves, right? We think about more magnons, and it's a different type of excitation and quasi-particles, right?
Thank you very much.